Alrighty, so today we are dealing with section 6.1, which is, as I mentioned last time, about the normal distribution. And this is an example of a continuous, or uses a continuous random variable, which is just like a discrete random variable, but the values but the variable part of it is continuous. Right? So in other words, you're not skipping over gaps. We're not talking about counting numbers anymore. We're counting everything. Right? Which means that even more so than the problems we did last time, last chapter, we really need either a calculator or a table to help us out here when we're finding the probabilities, right? Before, we could do it the long way. We could have used the formula and we could have added a whole bunch of stuff together, and we could have always done it the long way. But using things like binomial PDF or binomial CDF or Poisson PDF or Poisson CDF are much more efficient. Right here for continuous random variables, we're going to have to either use the normal PDF and normal CDF, or we're going to need to use a table. So I'm going to focus for these things. I'm going to focus on using the calculator, or at least writing out the commands that you would use on the calculator. Because the book can do a much better job of showing the chart, the table. In fact, your book includes one. And so we'll talk a little bit about it, but we're going to focus a lot more on using your calculator to get the numeric answers. So the thing that makes it normal is that it looks like a bell curve. It's symmetric, which my drawing definitely isn't, but we can pretend. So it has to be symmetric. And it's specifically symmetric around mu. Right? And it's bell-shaped. You can have symmetry but not be bell-shaped. And it's completely determined by mu and sigma. Right? So mu is obviously where it's symmetric about. Sigma tells you how wide it is. Right? But so if we want to talk about a discrete or not a continuous random variable being a normal distribution, right? We have to tell you what mu and sigma were, right? Binomial needed n and p. Poisson needed lambda. Normal needs mu and sigma, right? So the way that we get these probabilities, and the reason why it's hard, let me see if I can draw it a little bit better, right, is, well, for one, probability that x is exactly equal to something is 0. Right? There's an infinite number of possibilities. Picking out one individual one of them gives you 0 probability. Right? All of our things are going to look like maybe the probability. So let me get some colors in here for this. So maybe we have the probability that x is less than or equal to x. And one thing to note is that this is the same as saying the probability is x is strictly less than, right? It's not like our discrete distributions, our discrete random variables, where those were very different, right? We had a bunch of tips and tricks. And by a bunch, I mean we had one. We had a way of dealing with it. But they were definitely different. In this case, these probabilities are exactly the same. And what we get for it is, if this is x, then the area of stuff that I'm coloring in right there is the probability, right? If we wanted to find the probability that x is greater than or equal to y, well, that's going to be the same as the probability that x is strictly greater than y. And that's going to be finding a y, or putting y here on a chart and saying that it's all of this area. Right? And then if we want to know the probability that little x is less than, again, that's a horrible color. Let's see if I can't make a nicer green. There we go. That one's more visible at least. So the probability that our random variable is between x and y is going to be this area, right? Now, we don't have nice formulas, right? We can find the area of a square or a triangle or a circle or any of that stuff just fine, but we don't have nice formulas for finding the area under a bell-shaped thing, right? If you've taken any calculus and you're familiar with the terms, we can do that with something called the integral, right? If you take stats with calculus, you can do a lot more stuff here with continuous random variables. Normal is still a little bit tricky. But with continuous random variables in general, you can find those probabilities by taking integrals, but we are not going to deal with integrals. We are doing stats without calculus, so we're going to use our calculator and tables to figure out what that area is. So let's see. One sort of problem we can do is, let me draw up a bunch of different bell curves. And so let's give these numbers so I can go back to having a black pen. And so just looking at these guys, we can't figure out any probabilities, but we can tell some things, right? So I know that 2 has the biggest sigma, right? Because it's sort of the widest, at least the bell part of it is the widest. 2 and 3 look like they have the same mu, or at least close to it. I was trying to draw something where it's sort of centered around this point. 1 has a smaller mu than 2 and 3, right? Because it's further to the left of them, so mu is going to be smaller. And so we can tell that sort of thing, right? The wideness of the bell part of it tells us a little bit about sigma. Its position on the number line, right? Because technically there's a number line here. Tells us a little bit about where mu is. Yeah, so that's the basic idea of what we learn here. Next section is where we start to get into finding some of these probabilities, right? So I'll see y'all next section.